Question 4. Oop, no, 4. Good, right. Okay, what have we got here? Right. Carbon-14 is a radioactive isotope that occurs naturally. Scientists help is okay, so far so good. Techniques called use the idea of half-life. Right, what is half-life? Half-life. Time it takes for half of the undecayed nuclei to decay. That sounds right. Is that right? That's right. Okay, it's not these ones. It's not time for all the undecayed one. That's rubbish. Not for all the da-da-da. They're all rubbish. It's A. Right, move on. Sketch a graph to show how the activity of a radioactive isotope changes with time. Use the axis below. Okay. First of all, let's label our axes. We're going to call this activity. Other things you could call it if you wanted to, becquerels or count rate or any of these things. Activity is fine enough, and this is going to be time. Now then, I'm going to reintroduce you to your what should be a good friend of yours called the ruler. Okay, and what I'm going to do is I'm going to be cunning. I'm going to mark off some points on this graph every. Oh, this is inches, isn't it? Gosh, right, inches. We'll do that, and we'll say that this is 1 half-life, this is 2 half-lives, this is 3 half-lives, blah blah blah, etc. You get me? Good. This, I'm going to use the ruler properly, and I'm going to measure. Here we go. Look at that. That's 7 centimeters long. So if I go to 3.5, that's half of that. If I go to half of 3.5, is about what? It's about there. Okay. And then I'm going to estimate another half there. Good. So, gosh, that's the way. Good. I'll start there. After 1 half-life, it's going to come to here. After the 2nd half-life, it's going to come to here. 3rd half-life, it's going to come to here. Okay. And we want 1 smooth curve. Use a pencil. Use a pencil. Okay. 1 mark. And then 2 marks, 1 for a nice curve, and the final one, it can't meet the axis. Okay, it's just going to halve and halve and halve forever and ever and ever and ever, blah blah blah. Okay, if it meets the axis, you're going to lose a mark. Good, 3 marks there. Sorted. Okay, the most bizarre question in the world: a scientist investigates an old wooden comb. The activity of carbon-14 is 0.55 becquerels. The estimated age of the comb is 11,400 years. The half-life of carbon-14 is 5,700 years. Right, look at these 2 numbers. Isn't it a strange coincidence that this happens to be 2 times the half-life? Calculate the activity of the carbon-14 when it was new. Right, okay. Working backwards. Okay, when it was new, it was very radioactive, and then after 1 half-life, it halved, and then after 2 half-lives, it halved again, and so we have to do the exact opposite. Now, at the moment, in real time, we've got 0.55. We must times that by, let's get this right, by 2, and then we must times it by 2 again, because, yeah, and that will give us 2.2 becquerels, okay? It's a half-life question in reverse. If we'd have started off and they'd have said, okay, when it was new, it had a half-life, it had a count of 2.2, how much radioactivity would there be after 2 half-lives? After 1 half-life, it goes down to 1.1, and after another half-life, it goes down to 0.55. Okay, easy peasy. 3 marks for that. 3. Gosh, mark scheme. Where do we get the 3 marks from? Let's have a look. Let's have a look. Idea of 2 half-lives. Okay. Oh, I wrote that up there. You could write it here. Look, there you go. That's 1 mark. Idea of having the activity, halving the activity twice. So that's that bit there. And the calculation, right? So yes, And mark scheme says that if you just go straight in for the answer, then you get 3 marks. But always show your thought processes, okay? So you might pick up marks if you make a cock up on the calculations. Right, okay. Steaming ahead. The scientist takes several readings of background radiation. This is the radiation which is all around us, from space, from rocks, from food, from air, all that, and so on. Explain why this is necessary to improve the accuracy of the investigation. Suggest, explain. Gosh, 2 marks. I would say several readings are needed because a background radiation varies. It's not always constant. It's not always constant. It goes up and down, so we always take an average. Okay, so we can work average out if we wanted to. Okay, that's getting me a mark. Okay, and also we need to know the background radiation, so we can subtract the background radiation from our results. So we actually subtract it out, and then what we're left over with is the actual activity. Okay. Right, let's move on, because I'm losing the will to live. Okay, old objects like the comb emit very small amounts of radiation. Okay, very tiny. The activity from the comb is about the same as what comes from background radiation. Yikes, that means it's very hard to distinguish, doesn't it? Yeah, you can't tell it apart from the background noise. Scientists have stopped measuring the activity. Okay, right, so what are they doing instead? Instead they can measure the mass of undecayed carbons left over. So instead of mucking about with a Geiger counter trying to read these really small figures, you just actually weigh the carbon at 14 atoms. Suggest a reason for this change. It's only 1 mark. Suggest a reason. Gosh, I don't know. What would a good reason be? Here we go. Lots of reasons. Okay. It's hard to measure the radiation. It's hard to measure because it's really small. Okay. Here we go. Background radiation drowns the results. Okay, it gets in the way, a bit like noise, a bit like all the noise in the background and so on. Okay, and I guess we could say, I don't know. Let's have a think. It's going to be more accurate, because you can actually measure the smaller amounts of radiation just by weighing the atoms. Okay, so any sensible suggestion? Now, I'm just looking at Mark's scheme, and Mark's scheme says ignore better method or results are more reliable. I don't think that's fair. I think it's a more reliable method because you'd be getting repeat results, but they say ignore that. They do say difficult to distinguish between the reading and the background. We've said that anyway. Okay, right. Let's move on.